Hello, everyone. Welcome to another episode of History of Science and Technology Q&A. It's my chance to tell you guys things that I might know from personal experience about history of science and technology, or things that I've researched about that. And I'm happy to talk about both specific questions and general topics. And let's see, we have all sorts of questions saved up here. There's one question from Aaron. In 800 years, what will people call the methodology of a new kind of science? It's an amusing question. So my big book, A New Kind of Science, which is about to be 20 years old, sort of the big point is the study of simple programs and what they do, as distinct from using things like mathematical equations as the raw material for making models of things like the natural world. And well, let's talk about the history of the naming of things that describe the natural world. So back in antiquity, sort of talking about nature was, I guess, a branch of philosophy, although I don't think philosophy had really been given that name at that point. Aristotle, for example, had a book called The Physics. And I think in those days, if you look at, for example, Galen's work in first century AD or so, I think, he has books about medicine, physiology, that are also books about what we would now call physics, the nature of the natural world, so to speak. And I think that there was a strange sort of intertwining of sort of the natural world of how us humans work with the natural world of how rocks and so on that work. So I think sort of back in antiquity, kind of no great distinction made between sort of the figuring out of how things work. So it's worth understanding that in those days, kind of the notion of science wasn't really quite the same as the notion of science today. I mean, there's the question of how do you figure out how things work? What kinds of things? Things like arguments that people make about that turn into things like logic in the hands of Aristotle and so on, or how things work as in, how a plant grows or how life is formed, those kinds of things. Now, for Aristotle, for example, who was a great cataloger of things, a cataloger of, types of mollusks, and a cataloger of types of arguments and logic, and a cataloger of causes of things and so on. As that sort of great cataloger, sometimes he would make arguments about how things work that were what we would now consider philosophical arguments. And sometimes he would just make statements about this is how this kind of organism grows. Sometimes those were right, sometimes those were wrong. But the notion that one would just use one's everyday experience and one's powers of reasoning to work out how the world works, that was kind of what was assumed to be the way things were set up. And for, I would say, a very long time, that was kind of the Aristotle's work was viewed as sort of the canon of, beyond religious texts, that was kind of viewed as the canon of knowledge that was being passed down. And I think that the idea that the way the world works is something that you can either make just general observations on or you can reason about was kind of what was assumed. It wasn't assumed that there was a big tower. It was kind of like either you dissect the frog and it has this thing in it, or you reason about how the frog must jump this or that way. It wasn't expected that there was a large kind of formal tower that will be built where, for example, one would do things like one might do with modern mathematics or modern computation, where you would start from some set of rules, let's say, and you build this big tower of consequences on top of that. It was much more kind of sort of direct. And I think that, and similarly, even with logic, which we might now think had many steps of deduction and so on, the logic of Aristotle and even through the Middle Ages was syllogistic logic, which was mostly you memorize certain patterns of arguments. And I think two famous ones had the acronyms Barbara and Celerant. And they were just things like, I don't really remember, maybe I've never known, kind of they're things like, you can say P and you can say Q and you can say not P. If P implies Q, then not P. What does that imply? That's a form of argument that you can give. And people would just sort of memorize structurally those forms of arguments. It wasn't what we would now expect to be the case, where it's kind of, given the rules of logic, you can build this giant tower of consequences on top of that. That notion, I think, didn't really exist in those days. Now, there was a notion of mathematics from Babylonian times, Euclid, things like that, had a notion of mathematics. That was a place where that kind of deduction really was done, but I don't think that was really connected so much into science. Now, subsequently, many, a couple of thousand years later, I should say that people like Ptolemy certainly used geometrical arguments to talk about astronomical phenomena, when eclipses would occur, things like this. That was in first century AD or so. But this notion, I suppose, that in science you can have, it's sort of an interesting question. Did Ptolemy, in his presentation, was very Euclidean, very much, there is this statement about, the Earth is in this position, the Moon is in this position, therefore there will be this number of eclipses per year when these things are rotating around. I think that in many ways that was viewed as being sort of a self-evident truth. Given that the Earth was in this position, it was going around the sun, the question of why was it going around at that rate? Why was the moon orbiting in this way, or the moon slowing down, or even things like tides were not something that was understood at the time, because in a sense, what I would say perhaps Ptolemy was talking about is just things are this way, just like a Euclid might say, one has a right triangle of this form, therefore what are the consequences of that? Ptolemy was like saying, the Earth is going at this speed, the moon is going at this speed, what are the consequences of that, as one might deduce them, like Euclid would have deduced things about pure geometry. The notion that there would be some kind of sort of explanatory story of like, why are there tides, I don't think was part of that thought. So I think then kind of physics, there wasn't really a term physics, except it's a rather confused thing. As I say, Aristotle had a thing called physics, but really the general category was natural philosophy. The philosophy, the reasoning about how nature worked, and reasoning was pretty much what it was. And the idea that one could like do systematic experiments, do elaborate formal deductions of how things worked in the world wasn't really a notion. I mean, the notion of sort of systematic experiment, that's often attributed to Francis Bacon around 1600, late 1500s. I think curiously, Francis Bacon, I think was more a courtier and politician than he was necessarily a scientist. And in a rather ironic turn, given what's happened 500 years later, the part of his sort of statements about, we have this notion of science, we have things which can be deduced to be true by doing science experiments, and they are definitively true because we proved them with science by doing these experiments. Part of his rhetoric, at least around that idea, was to use it in a sense for political purposes, to say, we discovered this from science, so you can't argue about it. It's not something where, in past times, people would have said, it's in the Bible, it's in some religious text, therefore it is true, we can't argue about it. And that was, when you're setting up a country or something, and you can say, we're operating under God in this, with these God-given laws, so to speak, then you kind of, one can feel like one's doing something where there's no argument about that. That's just the way things are. Just like when one might say one's dealing with Euclid or elementary arithmetic, 1 + 1 = 2 is just the way things are. There's nothing really you can argue about that. And I think what Francis Bacon was going for was sort of another track where it's just, this is just how the world works. We can do empirical science, we can discover this is how the world works, and then there's nothing to argue about. And he saw that as being something significant for sort of having a sense of authority in doing things like running countries and so on. And it's sort of ironic that 500 years later, we're somewhat subject to the same kinds of uses of science in these pandemic times, so to speak. This kind of, it's science, so you have to believe it kind of thing. Of course, that's not really science as a complicated thing. And some kinds of science, some kinds of, 1 + 1 = 2 kinds of things, yes, it has to be that way. But there is a lot more complexity in kind of what's really true in science and how you know what's true than perhaps people, the Francis Bacon model is just tell them it's science and they'll believe it type thing. But that's really not the right story. Now, I think then this kind of notion of you can do experiments, you can do systematic experiments. The thing that is not at all obvious, and it's sort of a fact about the world that one has to kind of, in a sense, perhaps, deduce, know is true, etc., is the idea that you can do a repeatable independent experiment. That is, that you can do an experiment on one part of the world that is independent of the rest of the world. So, for example, you do the experiment in Paris, you do the experiment in London. It's, if you control the environment of the experiment, it doesn't matter whether it's in Paris or London. You'll still get the same result. It is not self-evident that any independent experiments can be done in the world. It's not, in some areas of social science, that's even less clear, that you can do an independent experiment, that you can do something where the environment is controlled to the point where you do the experiment once, you do it again, you define the sort of the parameters of the experiment, and you can repeatably do the experiment. That's kind of a critical assumption of empirical science. And there are senses, even in physics, in which that's just not true. It's kind of like the Heraclitus line of, you never step in the same river twice type thing. Things have always changed. I mean, that's part of, in the end, in sort of our models of physics, and we can get into all kinds of quantum mechanics and no cloning theorems and so on in quantum mechanics of being very much related to this idea that there is a history to the world, and if you do something at one time in the history of the world, it will inevitably be different from doing it at another time in the history of the world, even at this sort of very microscopic level of physics. But I think in kind of the progression of kind of what one meant by natural science, or natural philosophy rather, that was a thing that, sort of the experiment idea came in, and then kind of the big thing, mid-1600s to 1687 and so on, this idea of mathematics as being something that could directly inform natural philosophy. And that led to the name of Isaac Newton's book in 1687, Principia Mathematica Principalis, what is it? I can't do the Latin, but the English translation is Mathematical Principles, Principia Mathematica, of Natural Philosophy. So the notion that Newton had was you can take these ideas from mathematics, essentially from Euclid, the idea of sort of a deductive system from Euclid, and you can apply it to natural philosophy. And that was kind of the big new idea. I mean, Galileo had sort of pieces of that idea and so on, but that was the big thing, was that you can take, you can actually build up a deductive system in natural philosophy. You can say, there is an inverse square law of gravity, and then deduce, the comets have to move in this way, the structure of the solar system is this, and so on. And that, that became the story of physics, and was kind of, that was the direction from then on out. Now, then classical physics developed from kind of Newtonian paradigm, mathematical equations. Newton worked out the equations of mechanics, of classical mechanics, subsequently equations of elasticity theory, deformations of solids, fluid flow equations, then mid to late 1800s, the equations of electromagnetism, Maxwell's equations, and so on, all very much in the same mathematical framework of differential equations that Newton had basically introduced. although originally Newton's notation and presentation was much more Euclid style, much more proposition, essentially axiom. Newton's laws for Newton were like axioms. The fact that, force equals mass times acceleration was kind of like, I think for Newton, like the idea, in Euclid, two parallel lines will never cross. There was kind of, I think, not, that this notion that you could have mathematical principles of natural philosophy was something that was Euclid. What was the status of what Euclid was doing? What was Euclid doing? What was he thinking of when he said two parallel lines could never cross? Was that supposed to be a statement about nature? Or was that supposed to be a statement of self-evident truth about a construction that Euclid was coming up with? I think for Euclid, it was effectively a statement of self-evident truth, because Euclid didn't realize that, 2,000 years later, people would start talking about curved space where two parallel lines can cross, and can intrinsically do so. So I think for Euclid, it was kind of like take our everyday experience that becomes self-evident to us, and then put it in axiomatic form, and then make deductions from it. By the way, the work I've been doing recently on meta-mathematics kind of informs that a little bit differently, but maybe I shouldn't get off into that direction right now. But then for Newton, the question was F equals ma sort of an axiomatic fact that was in the same status as Euclid's axioms, or was it something more in the Baconian tradition of we observe this to be the case? I kind of think Newton was going more for the Euclid idea. And in a sense, force equals mass times acceleration is at some level a definition of force. That's Newton's second law. But Newton's first law, an object stays in uniform motion in a straight line if not acted on by a force. I don't know what that is. That's a funny statement, because that statement, again, is a statement that is actually very similar to Euclid's parallel lines don't cross. It, in some sense, is assuming flat space and things like this. Anyway, I think the sort of the philosophy, the true philosophy of what was really being meant by these things, I think was only implicit at the time. But so then get into the late 1800s, where we've got the whole stack of capabilities of classical physics based on differential equations, and then comes, quotes, modern physics. And people are still, they'll have courses, but everybody has courses on modern physics. What is modern physics? Modern physics is a century old. Modern physics is the study of things like relativity, quantum mechanics, atomic physics, things like this. It is modern in the sense that it was not classical, in the sense that it does not go back to Newton. You could go back even further to Aristotle. That wouldn't be the kind of thing that is taught in physics today. There are phenomena that, if you look at one of the things that's been sort of interesting in the history of physics, is that there's sort of been these levels of, there's sort of Aristotelian physics, in which, for example, in particular, one of the significant things about motion in Aristotelian physics is, in order to get something to move, you have to keep pushing it. Whereas in Newtonian physics, Newton's first law critically says, if there isn't a force acting on something, it'll just keep going. If it's if it's not in a gravitational field, if it's out in a vacuum and so on, it just keeps going. Of course, in Aristotle's time, there weren't, I don't know what, air hockey tables or something. There weren't things where you could reasonably have very low friction and where things would just keep going in a straight line. In Aristotle's time, most things that moved, you had to keep pushing them. So it wasn't unreasonable for Aristotle to make the claim that motion is something that you have to keep pushing to make it happen, so to speak. So, but I think then the sort of the defining characteristic of classical physics, it's sort of physics where, I don't know actually what is the right, historically there's a well-defined kind of notion of the distinction between classical physics and modern physics is kind of pre-1900 physics and post-1900 physics. One can point to, it's kind of like, when do Newton's laws of motion no longer really apply, either because of relativity or because of quantum mechanics? But so that's been the kind of the idea of physics there, I am somewhat amused by the question of what in our modern, I was going to say modern theory of physics, but that would be a even more confusing thing. In the fundamental theory of physics that we've developed in the last couple of years, which is kind of another step beyond what was done 100 years ago in the development of relativity and quantum mechanics. It's kind of a lower level understanding of what's going on and a more global understanding of what's going on. It's paradigmatically rather different from what's been done before. And the question is, how long will it be before modern physics is called, let's say, 20th century physics or something, to distinguish it from what we now have, which I guess is 21st century physics. I think we're finally at the end, so to speak, in the sense that people have wondered for a long time, is there a bottom to physics? As you go down and down and down, do you end somewhere, or is it kind of this sort of infinite regress of there'll always be a better theory? And that's again been something when people have looked at theories in science. One of the things that's typically observed is we have a model, it works up to this level, but there'll always be a better model. I think in our fundamental theory of physics now, we reach the end. We have something which is vastly bigger, and our perception of it, our experience of the universe is a tiny slice of everything that's there. But I think we kind of know, famous last words, but I think we know what's there. I mean, I think this thing we call the Ruliad is kind of the ultimate story of what's there underneath physics and mathematics, as it turns out. So it's sort of an interesting historical moment because there's been this progression. Only, I would say, this idea that there isn't an end to physics. It's really probably 200-300 years old, not more than that. People before that just sort of said, well, we'll get to the end. People in antiquity were like, it's all made of atoms, and that's kind of the end. And even in times of, Descartes, for example, was talking about, maybe in 100 years, we'll know it all, so to speak. It's only a more recent thing as sort of we went from sort of classical physics and then we find out, quotes, modern, what I'm claiming now should be renamed 20th century physics. That's actually, people should rename those classes 20th century physics, not modern physics. In any case, but the question, so now, I think the original question that was asked was, what will the thing that I call the new kind of science back in 20 years ago get called a long time in the future? I'm sort of amused to note that some people were like, I think nowadays people would mostly say, what should one have called that book? The name A New Kind of Science is the right name for it, which is what I thought at the time, because as people kind of try and describe it, it's like, well, it is kind of a new kind of science relative to what had come before. But I felt very deflationary in some ways because Galileo had a book called Two New Sciences. Not actually sure what they were anymore, but A New Kind of Science is kind of only one of it, so to speak, relative to Galileo's two of it. But in any case, and I didn't do what Galileo did, although it's a very interesting sort of device. I mean, Galileo wrote, I think, that book in as like a play, as kind of a discussion between multiple characters. I think 3 characters there. And I have to say that the notion of kind of explaining things in that sort of Q&A format, I think is actually pretty powerful, and maybe I should try more of it. But in Galileo's time, I mean, I'm sort of, in a sense, the pure sort of Shakespearean aspect of it as a play. I don't know whether anybody's performed the Two New Sciences thing as a kind of as an actual discussion between people. It certainly could have been done that way. I'm not sure it was great literature in that regard, but it was a useful device. I think Galileo famously had one of his characters, I think, called Simplicius, who was kind of a simpleton who was sort of a proxy, people claimed, was a proxy for the position being taken by the Catholic Church at that time. I'm not sure. I think Galileo was a quite a small, red-haired, energetic, aggressive fellow, and who was I think quite sort of brash in his interactions with people, and I think that sort of carried over to his interaction with the sometimes rather backward, but sometimes not so backward theologians of the time. But I will say that in terms of what I call new kind of science, this exploration of the computational universe of possible programs, that is sort of a different paradigm from this mathematical paradigm that was kind of the Newtonian idea from 1687 and so on. That kind of led to the mathematical sciences and sort of the mathematicization of physics, for instance. The kind of what we're doing in modern times, one could think of as the computationalization of things like physics. But I think the pure basic science of what do simple programs do, that's a different kind of science. That's why I called the book A New Kind of Science, because that's sort of its foundation, is what do simple programs do? What is that? It's not mathematics. Mathematics is about, has ended up being about specific kinds of structures that are sort of accessible to humans in various ways, arithmetic, geometry, things like that. This idea of you just write a program, it's certainly not computer science. Computer science is a story of writing programs that are useful for particular purposes. We write a program for a purpose. It's actually not really a science in that sense. It's more a thing that is where one is using computers to achieve engineering technological purposes. The kind of this science of kind of what is out there in the computational universe of possible programs, that's what might have been called computational science if that name hadn't been taken for other purposes. So quite recently, I kind of came up with the name Ruliology to describe the science of exploring the consequences of simple rules. So I would say that I'm going to wait. I don't know how long it'll be before there are the first professors of Ruliology, but I think it will happen. And that field of exploring simple programs and what they do as a matter of abstract science, it's an extremely fertile field. And there's just so much to do. And it has the feature that when you deliver things, you get to apply them. It's a very upstream kind of science. It's a kind of science where when you discover something, it has many downstream consequences for many different purposes. A little bit like some areas of mathematics, where you discover something about some kind of differential equation, and by golly, that the application of that applies to all these different areas. So it's something where once you discover something about this pure basic science of Ruliology, you can then flow that down into many applications. And so I think that's a very it's sort of an area that kind of like pure mathematics is something that sort of has this consequence that it exports to all these different application areas. It's been a thing that hasn't really had a well-integrated kind of community. And we're going to be starting a thing we call the Ruliological Society, which is an attempt to pull together a lot of people and activities in this area. It's been kind of very interesting to see as we've looked through, what happened to all those people who in the 1980s started doing things like following up on early work that I did in this kind of area. People have built very interesting careers embedded in random departments of, whatever it is, pure mathematics, computer engineering, maybe physics, maybe something else. But they haven't really had a home. And that home, I think, will be part of that home will be the field of Ruliology. That's one piece. I mean, another piece of new kind of science is what I'm now calling meta modeling, which is the question of once you have a model of something with all its detail of how does a tree grow or whatever else, what is the essence of that model? What are the underlying primitives? What are the pure sort of computational primitives that underlie that model? Meta modeling is what kind of gives you a to-do list for Ruliology. And in a sense, Ruliology, the sort of the pure generation of simple programs, what do they do and so on, it has other analogies, and other analogies, chemistry. Chemistry, particularly in the late 1800s, it's a lot of let's study this compound, and so on. And then later on, it turns out, oh, we just discovered that compound is really useful for this particular purpose. Isn't it convenient that there have been 500 papers written about it, so we know so much about this type of compound? And that's the kind of thing that I expect will be happening a lot with Ruliology in going forward. But in terms of kind of the paradigms of science, I mean, both the sort of NKS paradigm of computational rules and their consequences, and now a new paradigm that's come out of the physics project of multi-computation and this kind of multi-threaded observer-based view of time and so on, that seems to have a lot to say about a bunch of fields of science. What will all these things be called? I don't know, hard to predict. I'm always curious about how people name things. And I have to say, with a new kind of science, I struggled for more than a decade trying to figure out what name should I give this, and ended up giving it a name that in some sense has to be an interim name, in the same sense that modern physics is an interim name. But I thought that since my goal was to write a book that would be sort of a thing at that moment in time, it wasn't intended to be a sort of a living thing, although it's certainly has stood the test of time very well, and many things have been built on it. But it was intended to be sort of a moment in time kind of thing, and so that's why I felt it was okay to give it a name that was, in a sense, a moment in time name. I mean, I'm always struck by things I noticed when I was a kid, like in Oxford, there are different colleges in Oxford University, and there's a college called New College, which is, I think, the second oldest college. It was called New College because it was new relative to the other one that had already been founded sometime in the 1200s. And I remember when British currency became decimal. I don't know if it's still the case, I have to look, but in 1970, the coins all said new pence, 5 new pence. And I wondered at the time, what will be the case? How will people view this in the future? It's new. It was from before I was born, type thing. And so it's funny how that term evolves. But I think as a representation of sort of a moment in time, it's a convenient word. Okay, lots of other questions here. Oh my, a lot of interesting questions. Okay, Parmenides comments about Ptolemy. That Ptolemy was sort of a necessary step before Copernicus and Newton. Yes, I absolutely think so. Ptolemy did, Ptolemy did a great job. He systematized observations of astronomy. There have been, the longest running probably the longest running scientific experiment ever in history was the Babylonian astronomical diaries that were, every day for 800 years, somebody in ancient Babylon made observations of the positions of planets and also the weather and the height of the river and the price of corn and things. But and they recorded them on stone tablets or clay tablets, and we have maybe 2% of those tablets. They were painstakingly reconstructed about 100 years ago from little shards in the British Museum and other places. There was about 2% of that 800 years worth of daily observations, and those daily observations were known to Hipparchus, and then 200 years later to Ptolemy, and that was sort of a basis for quite a few of his statements about how things had to work. Because if you don't get to observe a lot of revolutions of the furthest planet was known at the time was Saturn. Uranus was not discovered until telescopes by Herschel, it was it's a long, painstaking observation of many astronomical phenomena and of eclipses and things like that. But that was the corpus. There was this big corpus produced by the Babylonians, It's Hipparchus then had a star catalogue. It's still a matter of debate whether Ptolemy plagiarized his star catalogue from Hipparchus. Actually, my son Christopher's been studying that quite a bit and trying to figure out, can you actually statistically figure out, because there are proper motions of stars move around, and in whatever it was, 200 years or something between Hipparchus and Ptolemy, some of those stars will move a bit. Now, obviously, the observations aren't perfectly accurate, and there are a lot of things where you point something up and you have a kind of a ruler type thing, and you're looking at angles from that ruler as you point it up in the sky, and it's not completely accurate. But can you deduce whether in fact Ptolemy got his own star catalogue or got it from Hipparchus? But Ptolemy, particularly, his big thing was the Almagest. Ptolemy was, first of all, had these observations, and then had essentially a geometrical, these geometrical constructions of how things worked. And he had essentially an explanatory theory based on epicycles, based on kind of spheres rotating on spheres or circles rotating on circles of the motion of planets. And there were, oh gosh, I don't remember all the details of this, but there were an increasing number of hacks that had to be introduced to account for all the planetary motion that was observed. And there's what is it called? There's the question of where the circles actually, where are the centers of the circles and how does that all work? And it got a bit messy. Then there were later observations. I mean, people, I don't know, people like Regiomontanus, for example, that was 1400s, I guess, was really people had versions of Ptolemy's Almagest through for 1,500 years, and more than 1,000 years, 1,300 years, whatever. And there were these kind of astronomical, and there were all sorts of different kinds of, people cared about astronomy because it was important for navigation and so on. And it was, and there were astrolabes for computing. You'd make a different astrolabe for a different geographical location because it would have things about positions of planets and so on. And it was a thing for a long time. Now, when Copernicus came along, Copernicus basically observed you can make things a bit simpler in the Ptolemaic system by assuming that the Earth goes around the sun rather than the other way around. It wasn't really that different at some level. It was, and computationally, the state of the art in Ptolemaic epicycle computations was actually pretty good compared to Copernicus. And it was more of a kind of a detailed footnote, not quite footnote, but a detailed point that things were a little bit easier to understand, and it made more sense. You had less weird epicyclic hacks if the Earth went around the sun. And, Copernicus, I think, felt that, Copernicus was he was a kind of theologically oriented fellow, and thought that this idea that maybe our common sense that the Earth isn't the center of the universe might not be right. He thought, he knew that was a shocking thing, and ended up not publishing his De Revolutionibus, what is it called? That's the term revolution comes from that Copernican thing where his book is about the revolution, as in turning around of the celestial spheres, so to speak. But he didn't publish that until he was until after, well, it was published after he died. But I think it is an irony of these things that the actual method of calculation that we use even today for celestial mechanics, for computing ephemerides, computing positions of planets and so on, is pretty much epicycles. It's couched in different terms. It's couched as Poisson series and these kinds of essentially Fourier decompositions of these different terms of the piece that's associated with the motion of Jupiter and the piece that's associated with this. But in the end, it's mathematically very similar to what Ptolemy did. And so yes, I think unquestionably Ptolemy, Regiomontanus, these people were a necessary precursor to Copernicus. Copernicus then there was Kepler, and Kepler sort of cleaned things up even further, and I think that helped set the stage for, and Kepler derived Kepler's laws, which were kind of for planetary motion, which was something that Newton then got to explain in terms of his inverse square law and so on. That was sort of a Newton. There was kind of for Kepler, it was just, it is a fact, equal areas and equal times and so on in planetary motion. That was just a fact. For Newton, there was this kind of mathematical principles of natural philosophy. There was a deductive aspect to that. You could go from something lower level and deduce a fact like that, rather than it just being sort of an axiomatic claim. Let's see. Oh boy. Baker asks, when Newton invented calculus, Newton invented two things, calculus, well, several things, many things. Calculus, his three laws of mechanics. The question was, with our physics project, is it more like calculus or is it more like inventing new laws? That's an interesting question. I think that the first question is, what's the raw material of the universe? What kind of a thing is it? Is it, what is the raw data structure of the universe, so to speak? And that's a big piece of this project, is to elucidate what that is. And then there's a giant formal structure that's built on top of that. That formal structure has elements that are very much like calculus, that are very much like, how do you deal with this formal? The first thing is you have to posit that the universe has this data structure at the bottom, that it is the Ruliad, and that's the story. And that is something more like, that is essentially a natural law. Once you have that natural law, you are then looking at the sort of formal consequences of that, and then you're building up methodologies that, among other things, look like generalizations of calculus and so on. I mean, for us, Newton got to do calculus with one variable. Later on, people generalized that to calculus with several variables. We get to do calculus with fractional numbers of variables. That's just one corner of what we need to be able to figure out to understand how things work. And then the whole general formal structure of this thing we call multi-computation, that's, again, something where there's a large amount of formal structure that's sort of more analogous to calculus. The statement that there is this underlying data structure, there is this underlying Ruliad underneath physics and mathematics, that's a statement like kind of Newton's laws of mechanics. The other thing, which I suppose is a bit like that too, is the interpretation of that. What is an electron in terms of that underlying raw structure? That's kind of understanding that is something more like, that's a little bit more like Newton's definition of force. The notion of force is something which was a thing where that was something which he was sort of plucking out of what happens in the world and identifying this thing called force. Later on, the thing called energy and so on. I think one of the things that's happened comes out of new kind of science and so on, is this notion of computational irreducibility, for example, as a thing that you kind of pluck out as being important. I think that's a type of thing. What kind of definition should you give? Force, computational irreducibility, branchial space. These are definitions. There is an underlying reality, so to speak, but there are definitions of things that we humans consider useful to talk about for purposes of science and so on. Let's see. It's a question from Adiod. Why was gravitoelectromagnetism ignored for so long? I'm not completely sure what that refers to, but the question of how much is gravity like electromagnetism, for example, the laws of electromagnetism, by the time Maxwell had really put them together into Maxwell's equations in the 1870s, 1880s, that kind of time frame, that was pretty well established laws of electromagnetism, which had implications. Important implication was there should be electromagnetic waves. and then Hertz kind of was like, yeah, we can do an experiment to show that electromagnetic waves really exist. People asked him, what's that good for? He said, well, it's kind of an interesting experiment. Of course, that's what gave us radio, which has been quite important technologically. But the idea that something like the equations of electromagnetism should apply to gravity, that really was an outgrowth of Einstein's general theory of relativity. The idea that electromagnetism told you things about the world that were in the end incompatible with mechanics, with Newtonian mechanics. That's what led to special relativity. The fact that in Maxwell's equations for electromagnetism, the speed of light is a constant, whereas in mechanics, the way one had thought about that, a flashlight, if you're running at half the speed of light and you have a flashlight, the light should come out at 1.5 times the speed of light, which is incompatible with kind of the way Maxwell's equations work. And it was relativity that kind of brought those things into correspondence by saying that, well, actually, space and time are distorted, and that's why there's no incompatibility between Maxwell's equations and the laws of mechanics. But the question of whether there would exist things like gravitational magnetism I don't think that really came up. I mean, it could have done. It could have come up by 1900 or so. It could have come up. But that was the thing that was in the end a consequence of general relativity. And it had its important consequence was that when a photon goes around the sun, when light goes around the sun, there's a certain amount it's deflected, bent by pure gravity. But there's also gravitational magnetism. And because a photon is going at the speed of light, it has the effect of, so magnetic effects are proportional to velocity, and the magnetic effect is sort of maximal. And so there's a factor of 2 difference in the deflection of light around the sun between the Newtonian theory and the theory that includes sort of the theory of gravity that is in general relativity. And that factor of 2 was sort of the critical thing that was supposedly verified in the 1919 observation of the total solar eclipse by Eddington and friends in South Africa and so on. I say it's supposedly because it's probably that experiment was kind of fudged. But the result is true anyway. Let's see. Well, let's see. Zayden comments that they disagree with me that there's no end to how infinitesimal the universe gets. And there's always more discoveries and so on. Those are inconsistent. Those are different kinds of things. So the question of whether there is a smallest length scale in the universe is a completely different question for whether there's an infinite number of things to discover in the universe. The fact that there may be only a countable number of things in our universe, a finite number of things, 10 to the 400 atoms of space or something, that doesn't mean, okay, so for example, time might still go for infinitely into the future. So there's still infinite things in the universe. And the question of whether in principle certain things can happen in the universe, that's a formal question. That's not a question of whether the 10 to the 400 things that we happen to have in our universe, we can say, given the rules that those 10 to 400 things follow, if we were to set up this kind of configuration of those things, would we get a weird space tunnel, white hole combination thingy? Or is that just not possible given the rules of our universe? So that's a different kind of question. It's a kind of question where you're saying, does there exist a way of taking the underlying rules of the universe and arranging the setup so that essentially making a program so that it will have this or that behavior? That's a different question. And about that, there is undoubtedly and inevitably an infinite frontier. That is, there's always more to invent. There's always more to discover, because while it may be the case that drilling down, we got to the bottom. We got to the atoms of space. We got to the eames, as we're calling them, the kind of atoms of existence that underlie everything. We got to those. But what consequences the operation of those things have, that is an unbounded story. And that means that it's like saying, if we could ask, is there a number with this strange property? Well, we can't, we might be able to prove that there isn't such a number, but if we just are looking for that number, we might be looking and looking and looking, we get to bigger and bigger and bigger numbers. There's no end to numbers. there's no end to that, the question of whether that particular thing can happen. Now, we might be able to, with a finite theory, some deductive theory, some axiomatic theory of arithmetic or whatever else, we might be able to say, no, we can show that this particular property can never occur. However large the numbers you consider, there will never be one that has this or that property. What Kurt Gödel showed in 1931 is that with any finite axiomatic system, you can't expect that all questions that are of an arithmetic nature about like whether certain equations will have solutions or whatever else, you can't expect there will be a finite proof of all of those kinds of things. So in other words, it will be the case, essentially Gödel's theorem and everything we know about computation, computational reducibility, principle of computational equivalence and so on, those things basically establish the idea that it's an unbounded frontier, that there's always more to discover, that you'll never get to an end in what you can imagine. Now, the question of what's useful to us, that's a whole different question. The question of what we choose to make technology out of, we choose to discuss in science, those are questions that are sort of human determined questions. And that's something where there are different kinds of bounds that are put on it. But I think it's a quite separate question, whether there is a smaller scale to the universe physically and whether there is an infinite amount of stuff to discover about the world. Now, in terms of the smaller scale thing, I think there's a smaller scale, but actually in our model of physics, one of the possibilities is that the universe is always subdivided. Back in 1915, when Einstein wrote down his equations for general relativity and the equations for gravity and the structure of space-time, one of the consequences of those equations is that it predicted the universe would always expand. And Einstein was like, that can't be right. And so he added this thing called the cosmological term, cosmological constant, which was essentially a hack to prevent the universe from expanding in his theory. Now, he later said, so Hubble by 1920 or so had already discovered, in the 1920s at least, had already discovered the expansion of the universe. And so Einstein, his hack of adding this cosmological term was a mistake. So in kind of a possible repetition of that mistake, it is my immediate assumption that the universe does not progressively subdivide itself. But it is perfectly possible that the number of degrees of freedom, the number of atoms of space is continually increasing. The fact that let's say that every atom of space was dividing into two atoms of space, would we notice? Well, not really, not necessarily, because everything about us is relative to other things is staying the same size. But so one of the more exotic possibilities, which I have to say I haven't explored much in the last year and a half, but one of the more exotic possibilities is that the universe is continually subdividing. That is, that the number of atoms of space, which might have started as a very small number, it probably did in our models, it can increase, but it could be the case that it is increasing very, very rapidly and continually increasing, so that when you say, how many atoms of space are there in a meter? What is the elementary length? We might have an estimate. I have a rough estimate that maybe the elementary length is 10 to the minus 90 meters. That's very small, but it could be the case that at every moment in the history of the universe, the elementary length is getting smaller and smaller and smaller and smaller relative to a meter. In other words, the number of elementary lengths necessary to make up a meter is continually increasing because the thing that defines the elementary length is continually subdividing. So one of the most exotic possibilities, and when I say the most exotic possibilities, somehow often in the way that fundamental science works, the exotic possibility turns out to be the one that's actually true, the one that's right at the outer limit of what we imagine might be conceivable. But that possibility is the universe is continually subdividing. And so when you ask me, what's the length scale? What's the elementary length? I say, okay, let me think about that. Let me go and try and measure the elementary length. Let me try and look at some complicated black hole thing that is sensitive to the elementary length. Well, by the time I've made the measurement, the universe will have subdivided. So at every moment, if you say, I want to make a measurement which reveals the fact that that the universe is actually made of these discrete elementary lengths and so on. By the time enough elementary times have gone by, I can measure that elementary length. I'll be wrong about the elementary length. And whenever I look to see, show me the discrete elementary length, by the time I've observed it, it's subdivided. So in a sense, to my observation, the universe will look continuous. It will look as if it has no lower limit on size, because every time I try and measure the lower limit on size, it will kind of run away from me, and it will have subdivided further. And so that's kind of a bizarre possibility, the bizarre edge case of does the universe have the smallest length scale or not? Is, well, it does at every moment in time, but the length scale is continually relative to the fixed size of a meter, our experience, our definition of a meter, it's always continually subdividing. Let's see. Other questions here. Okay, there's a question from Pressure. They say, I understand a great deal of human history was lost in ancient Alexandria. Of the early mathematics, are there texts that reference concepts that are lost to us? Interesting question. So, I mean, first thing about Alexandria, the Library of Alexandria, sort of one of the, you could think of it as an organized university-like thing that was centered around a library where it was a large collection of scrolls. And I think it's often people in being negative about different conquerors of Alexandria in Egypt, people would say either that Julius Caesar was responsible for the burning of the Library of Alexandria, or that that Islamic invaders centuries later were responsible. It is true there were various fires at the Library of Alexandria, and certainly scrolls were destroyed at that time. I think there were two different sites, and one near the harbor where I don't know my history very well here, maybe 56, 7 BC, I don't know. The time of Cleopatra and Julius Caesar and all that. And I always like the fact that Cleopatra was, while not having the strongest force, had the most, wanted, the sails of her ships dyed purple, which was a difficult color to get because it was from crushed beetles and so on, because it would be a more dramatic presentation, at least when the invaders showed up. That's probably an apocryphal story that may not be accurate, but it's often, a lot. The Library of Alexandria didn't make it to modern times. In fact, in the end, there were, most of the, we don't have original texts from antiquity for the most part, unless they're on stone inscriptions. We have typically copies of copies of copies, and occasionally something will be discovered where somebody used a sort of wrapping paper, or as a reused paper, where it was, originally somebody had written out a version of Ptolemy or something, and then somebody had written over it some kind of trashy novel, or they weren't quite novels, but trashy book of the 1400s or 1300s or something, and then it's discovered that actually there's some great text underneath, and many texts were thought to be lost. I mean, like Cicero, for example, I think was known as a historical figure, but it was not known that his works had survived. I think they were discovered in the Vatican Library in the, I don't know, 1800s maybe, if I'm remembering correctly. And there are lots of things in that people reference, like, for example, Cicero references a sort of mechanical calculating device. The Antikythera device is the one example that we have. It came from a shipwreck off Greece, from sometime between the 1st century BC and 1st century AD. And that's the only example we have from antiquity of a mechanical calculating device, but Cicero mentions that. I think, who mentions that? Somebody, a lot of things, for example, Troy, the city of Troy in the Iliad, was thought to be sort of maybe fictional until the 1800s, when Schliemann and friends, excavated Troy. They made some mistakes in excavating it because it had many layers, and they kind of blasted with was it dynamite or gunpowder at that time? I'm not sure. Through layers of what were probably the Homeric Troy, but in any case, Troy was thought to be something that didn't really exist, but turns out it did. I mean, the other one is Atlantis, the lost city of that sort of went below the ocean type thing. What was that? Where was that? It was a city that was partly described in terms of a sort of utopian character to it, but was it a historical city? Where was it? We don't know. A surprising number of the things that were mentioned in these texts in antiquity as kind of things that were being referred to have turned out to be real in some sense. So, many, for example, Euclid, he wrote a bunch of books that are lost. I think he wrote one on optics that's lost, and a variety of other kinds of things. I mean, one thing that is often the case with like Aristotle, for example, many of his works survive. I don't know what fractions survive, but sometimes there are pointers. I mean, for example, somebody like Democritus, I believe none of his works survive. And none of the pre-Socratic philosophers, very few of their works survive, if any. And mostly they're known by references, often rather negative references, that were made to them in subsequent works. So a question is, are there other pieces of mathematics that were sort of known in antiquity that really aren't known today? My favorite possibility would be that somebody did cellular automata in 500 BC or something, and we'll finally find the mosaic. If you look at Babylonian tablets and you look at kinds of things they were calculating, we have lots of tablets and they calculate lots of things. We don't really know completely whether those were school exercises or advanced mathematics. Probably they were kind of school exercises. But for example, there are a bunch of geometrical figures. For example, they like very much lunes, kind of arcs of circles, pairs of arcs of circles, and questions about the area of a lune. And they also had a thing called it's translated as the cow's nose, but it has a nicer name in Latin. But it's a combination of four, sort of a cusp, these four cusps made from circles. That was a thing that features quite big in the kind of Babylonian mathematical exercise books. And it's something that nobody talks about that today. The thing that, so in terms of kind of major areas of mathematics that have been lost, interesting question, what might they have been? The Pythagoreans, for example, had a sort of a thinking about mathematics that was at one level sort of modern, talking about numbers and ratios and irrationality of the square root of 2, and at some level, bizarrely non-modern. I mean, they thought every number, 1 through 10 had a significance, male, female, this, that, and the other, different numbers represented those things. And they thought it was very significant that they called it the tetractys, I think, 1 plus 2 plus 3 plus 4 equals 10. Okay, they thought that was a very significant fact. We don't care about that fact these days. That's not something that's sort of a front and center fact. They also, they looked at numbers like primes. I think they knew about primes. They also knew about perfect numbers, numbers which are the sum of their divisors, except for the number itself. But perfect numbers, whereas primes have been an important building block in many things done in mathematics and in theory of numbers and so on, perfect numbers have been much less important. I mean, Mersenne primes are kind of a meeting ground of perfect numbers and primes, but generally perfect numbers are just not something one talks about very much. And for example, the question, I don't know, are there any odd perfect numbers? That's been an open question in mathematics from the time of Pythagoras to now. Were there things? So there were things which people cared about then, like the perfect numbers and so on, which we don't care about much today. Are there things where we would say, wow, that's an amazing discovery? In mathematics, I'm skeptical. I think that we've picked over the obvious mathematics, probably. the thing that would probably be the most dramatic is a sort of essentially a Ruliological discovery that one could take these rules and make this pattern. Now, one thing I noticed just recently, there was a collection of Babylonian tablets that have been found that showed different kinds of maze designs. And it's very unclear what those maze designs, how they were generated, why those particular designs and not others. Was there some enumeration that was being done? Was it just, oh, this was a doodle, that was a doodle, and so on? We don't know. And I mean, I have to say, going back to other kinds of things, even in archaeology, it's like you see these things. I mean, we're fortunate from ancient Greece, for example, even from ancient Babylon, that there's enough of a continuous thread of history that we understand well, and when there's written language and so on, we have some context for understanding what were these people talking about. You know, when we see, you know, the random handprints on the cave paintings from, you know, whatever, 10,000, 20,000 BC, things like that. What do these mean? We don't have the slightest idea. Were they just somebody, you know, sort of trying to wipe paint off their hand, or were they some kind of important societal thing of, you know, let's like a visitor book or something, let's all put our hands here to show we visited the cave, or who knows what. I mean, that particular thing is probably knowable because we can see whether they're similar hands or not. But, you know, what, or was it a game that was being played? Who knows? We don't know. We can't project backwards from what we know today to those things. So is it possible that there were sort of forms of formal thinking that were done in antiquity where we don't where we don't have a connection today to those things? Yes, I think that's possible. I think that, for example, I could imagine, well, I think we would often call those things art. We would often say, oh, there's this thing, it's a geometrical figure, it's a, you know, it's a flint. Well, sometimes we call it art. Sometimes we might say, you know, this was a, yes, I mean, we could imagine, you know, there's a flint that's been napped in this particular pattern. Oh, that turns out to be an incredibly clever pattern if you're trying to, you know, I don't know, put a, you know, have it fit in the bark of a tree when you throw the thing on the end of a rope or something like that. And it's something where we don't understand that discovery today. So are there possibilities that there were things like that where people said this was a significant thing in mathematics? I think my best chance for that will be something from Ruliology, something from simple rules. You know, you follow my Rule 30 cellular automaton, you follow that. That could have been done perfectly well in antiquity. Probably it wasn't. We don't know that for sure. And you know, had somebody excavated some collection of stones that were in this pattern, they just said, oh, these are randomly placed stones, as opposed to, wait a minute, we can see there's this rule to determine how those worked. Okay, I'm going to, a lot of other interesting questions here, maybe for another time. Aaron is asking, is Ruliology a young person's game, an old person's game, something else? What traits do you think will be important for great Ruliologists? You know, it's a new field. New fields aren't one of the remarkable things. I've been involved in a few new fields, new areas, new developments, and one of the things very interesting about them is that people sometimes say, oh, it's only the young that get involved in new stuff. It's not true. It's not true. It's a distribution of ages. And what often happens is new things come along, and those things are a great fit for a particular person. And they just fit in with the way people think, the kinds of things people like to do. And, you know, one is lucky if the things that are that great fit happen to be aligned in history with when one's alive. And, you know, for me, I've been pretty lucky that computation and things around the ideas of computation, you know, my sort of time in history, so to speak, has been well aligned with when, you know, computers started to be usable for general purposes and so on. And so I'm pretty happy about that. But you see, when new ideas, new methodologies emerge, there's usually a distribution of ages of people who get involved, because there are people where, you know, they might be in their 50s or 60s or 70s or whatever. And it's like, wow, this is a thing that really fits with a particular way of thinking and so on. So what will make great Ruliologists? I think it's there's a certain clarity. Ruliology is about, if you are always trying to hack things and you're always trying to say, oh, I'm trying to, I'll add this little piece, I'll see what happens if I add this thing to the rule, et cetera, et cetera, et cetera. That is not, I think, the best Ruliology. I think the best Ruliology is drilling down to the essence of things, where you're looking at the simplest rule and the simplest this, that, and the other. So I think this idea of being able to sort of drill down to the essence of things, having a kind of clarity of thought that makes one kind of drill down to the essence of things, I think that is an important feature of Ruliology and being a good Ruliologist. I think that goes along with writing, Wolfram language is sort of the language of Ruliology. And I mean, it's we can, in principle, encode rules for any computer for things that aren't even computers. But in a sense, after I've spent 40 years doing sort of Ruliology and doing Wolfram language, it's a tower that's really built very ideally for that purpose. And there's the question of, is it an elegant Wolfram language program, or is it a hacky, complicated program? And that, I think, is an important feature for Ruliology, is make an elegant program. In fact, a person I know, a mathematician, just sent me a couple of days ago a piece of essentially Ruliology, where he'd written a piece of the Wolfram language program was pretty good, but a piece of it was kind of messy. And so I pointed out, it's literally one function. It's one thing. It's just fold of this, this, this. And when you see it's that, you understand what the system is doing much better than when you see the thing as some kind of loop and it's doing this and that and the other. So it's kind of that sort of clarity of thinking captured in this computational language, I think, is an important feature of Ruliology. What are the simplest rules? Capture them in the simplest way, represent them in the simplest way, and so on. Then the next thing is, you got to be a good, I would say, almost unemotional experimentalist. That is, you run the programs, you see what they do. You may have a prejudice about what's going to happen. You may choose to run particular programs because you have an intuition about what might happen, but you have to be very kind of hands-off and unemotional about what you think is going to happen. Because, my oft-given quote is, the computational animals are always smarter than we are. Whatever you think might happen, it will turn out that there is some way that this little computational system will end up doing something unexpected and more complicated than you imagined. And so the ability to kind of to sort of do experiments without forcing your conclusions on those experiments, that's an important thing. And that's sort of a psychological turn of mind that is in different fields of human endeavor. There are different levels of value to that kind of turn of mind. I mean, sometimes it's like, I believe in something, and so that's what's going to be true, independent of damn the facts, I'm just going to show this is true type thing. That's a different kind of thing than doing this type of essentially empirical science, where you are continually humbled by what's actually true, and where you continually realize you didn't expect the things that actually turn out to be true there. I think another feature is is that sort of, just as there's clarity in the setting up of rules and so on, there's also a question of clarity in the presentation of things. And I think, our eyes are a very high bandwidth, our highest bandwidth way of kind of getting stuff into our brains, and being able to make good visual presentations of things is a very useful asset in Ruliology. And sometimes, with some things like, I don't know, cellular automata, it's well, I mean, I guess that's sort of a, the fact that I picked one-dimensional cellular automata, which have a very clear visual way of being represented and so on, that was very important for sort of the early developments of Ruliological ideas. And nowadays, with a physics project, we're dealing with these kind of multi-way graphs. It's rather a lot harder to get those things into human brains. They're things that don't as naturally kind of just like, I see it, I know what the pattern means kind of thing. And so that's sort of a challenge, but it's something where, as you pick away at that, kind of being able to have creativity about those kinds of things is important. I think the what other aspects? I mean, I think that really it's this sort of clarity of presentation. I mean, Ruliology lends itself to kind of very at the bedrock level, elementary, explainable, simple to describe kinds of things. More so than mathematics, for example. Mathematics, somewhere deep inside the system, may be something simple to describe, but one often builds big towers on top of that. The best mathematics is ultimately quite simple to describe when it's described in the right terms. But there's a lot of how you get there that ends up being very ornate. In Ruliology, much of that ornateness is inside your computer, not in what you have to be exposed to. I suppose another thing is, insofar as some part of the story of Ruliology is generating computationally irreducible behavior, where you pretty much, you have this rule, you just have to run it, see what happens. But there also is the question of picking away at it to find sort of computationally reducible corners, things where you can actually make statements based on traditional mathematics and so on. And there's sort of a question of, well, what kind of mathematics? And pretty much it's discrete math, combinatorics, those kinds of things. Most of the time it's needed, although with smatterings of other areas. And maybe in some of the things we're doing now, maybe category theory, higher category theory, some of these kinds of more algebraically derived mathematical ideas may turn out to be sort of important, even at the level of Ruliology, as a way sort of to organize the thinking about these kinds of systems. But that's a really good question. I think, yes, the question of what the name, a Ruliologist, I think Ruliologist is the right name. I think Ruliographer is probably somebody who catalogs. A Ruliologist is probably somebody who studies. A Ruliographer is probably somebody who writes down and catalogs the rules that are out there and what they do. And that's sort of a separate thing. Great. Well, I think that probably exhausts our time for today here. I look forward to doing this again in a couple of weeks. And actually, I have another live stream coming up in 5 minutes as part of my day job, looking at Wolfram language design. I like to also remind people that, I should give plugs for a couple of things. In case people don't know, I do write a certain amount about sort of history of science and technology. And there's a book I put out that's a collection of things I wrote called Idea Makers, which is historical biography. I haven't done, when did I last do a historical biography? Maybe a year ago or so. There's a bad correlation. Well, there's a good and a bad correlation. And sometimes I do those things when there's a n-100th anniversary of some event. Sometimes I do them about people I've known as kind of obituary pieces. But you'll find on my writings.stephenwolfram.com, you'll find a historical section where there's all kinds of different things. And some of what I've talked about, people were asking about Ptolemy and so on. I wrote when the eclipse, total solar eclipse that was visible from the US happened a few years ago. We had built this website that predicted to the second when the eclipse should occur in a given place. And as kind of a background to that, I wrote a long historical piece about history of astronomy and prediction of eclipses and so on. Anyway, I was going to say the other thing I was going to say was that I think there's a form on the web that allows people to submit topics and questions that they'd like me to cover in these live streams. And please feel free to do that. And I look forward to addressing more things another time. Great. Well, thanks very much and